In the second half of the 19th century, the German chemical engineer and hygiene pioneer Max von Pettenkofer formulated the concept of natural self-purification. With this term, he referred to the biological degradation of contaminants and pollutants in water bodies using the metabolic properties of bacteria and other microorganisms. In simple terms, microorganisms use contaminants as food and thus convert them into water, carbon dioxide, and nitrogen. This gave rise to the question of how much contamination a river or water body can absorb before it stops purifying itself and excessive pollution, also known as eutrophication, takes place. Max von Pettenkofer also demonstrated the connection between hygiene, drinking water quality, sickness, and the spread of diseases. To support his theses, he exposed himself to cholera in a self-test and survived it without serious health consequences. His ideas led to the construction of the first sewers and wastewater treatment plants, initially in cities only. Today, every biological wastewater treatment plant uses the natural self-purification process described by Pettenkofer. A difference to naturally occurring water bodies is that in wastewater treatment plants, a near-perfect environment can be created for the bacteria and microorganisms to thrive. This increases their number to a maximum and highly accelerates the natural self-purification process. The size of a treatment plant depends on the amount of wastewater occurring. Typically, the wastewater to be treated stems from domestic, municipal, and industrial use, as well as from rainfall. Wastewater contains dissolved and undissolved substances, which can be of organic or inorganic origin. In some cases, wastewater also contains heavy metals and salts, which are dissolved in the water. Here you can see our modern wastewater treatment plant in Halle. Let's take a closer look at its structure. The treatment plant consists of 3 areas: mechanical treatment, biological treatment, and sludge treatment. Mechanical treatment starts with a screen, followed by a sand trap and grease separator. It finishes with the primary clarification. The aim of mechanical treatment is to remove all floating substances and solids from the wastewater. The screen filters coarse solids out of the wastewater. It consists of fixed bars arranged at a defined spacing from one another. The raw wastewater flows through the screen. Coarse solids are held back by the bars. A vertical removal device pushes them onto a conveyor belt to be transported away for disposal. The wastewater then continues to the sand trap, which can be either an aerated or a round type. Here you can see an aerated sand trap. Air bubbles rise from an aeration system mounted on the tank floor and make their way to the top. This results in a vertical flow impulse in the tank and makes the wastewater rotate vertically, which separates heavy particles such as sand. Once these particles have reached the bottom, they fall into a drain channel, also called a sand trap channel. A scraper then pushes them into a sump, and some kind of pump transports it away. Let's look at a round sand trap. In this case, the so-called teacup effect is used to separate the sand particles. The wastewater entering from the side generates a circular flow in the round sand trap. Due to the velocity distribution, sinking particles are automatically transported to the center of the tank and discharged into the pit. The so-called Venturi effect transports the sand out of and away from the discharge pit. Which sand trap to select depends on various factors. Generally speaking, the round sand trap is more commonly used in smaller wastewater treatment plants. The next step after the sand trap is the grease separator. Grease can be separated in either round or a rectangular tank. The principle is the same for both tank designs. Grease accumulates and stays on the surface, from where it is later skimmed off with a scraper. The pre-treated wastewater is now guided to the primary clarifier. The primary clarification tank can be of round or angular design. Here, too, both work according to a similar principle. Light substances contained in the wastewater accumulate on the surface, whereas heavy substances collect at the bottom of the tank. The substances are pushed together by a removal device and then transported to the sludge treatment stage. Round primary clarification tanks are designed with a rotating bridge with a scraper. The scraper pushes the heavy substances to the middle of the tank, where they are discharged into the pit and transported to the sludge treatment stage. Light substances are skimmed off the surface. In angular primary clarifiers, a sliding plate moves from the left to the right and back again. When the sliding plate travels to the right, it collects all floating substances up to a fixed plate. Everything that sinks to the bottom of the tank is then pushed into a pit by the sliding plate moving to the left. From the pit, the sludge is pumped towards further sludge treatment. The wastewater continues to the biological treatment stage. Now that all coarse solids have been removed from the wastewater in the mechanical treatment stage, microorganisms, anaerobic, anoxic, and aerobic bacteria serve to decompose dissolved substances contained in the wastewater in the biological treatment stage.